A few announcements for the class one. Quiz one was returned, and I did forget to upload the solutions. Those are uploaded now if you want to compare what your results were, your answers were with the solution guide. So if you have any concerns with that, with the comparison or how the points were divided up, contact Jonathan first. He did the grading for the quizzes. If you still have concerns after that, then you can involve me with that. Lab 2 was due today. A couple groups had some issues, have some extensions. So I probably won't be posting the solution guide for Lab 2 until those are in later in the week. I'll make an announcement when the Lab 2 solution guide is posted, because that will be important, I'm sure, for you guys studying and preparing for the quiz number 2 for next week. And then the last thing, and I'll also emphasize this at the end of lecture as well, I've included a Google form at the top of the module section in Canvas, just for any feedback that you guys have on the course so far. It is an experiment this semester with the remote and in person in the lab. So I appreciate any feedback that you have regarding that, what's working, what could maybe be improved with some small changes. And also I'm just a little curious of what resources you guys are using. So if you want to provide some anonymous feedback, feel free to do that this week as well. So before we get into lecture, any questions at all? Okay. And people that called in a little late, I did make a couple, not critical announcements, but this will be all uploaded on YouTube if you want to hear those. So let me share the screen.
I have a question about submitting the lab. You said that you prefer you prefer it to be in Microsoft Word, but I tried submitting it and Canvas said that they only accept .pdf for some reason.
Yeah, for the submission, submitting it in PDF. I don't know if I ever said anything with Word.
Maybe I imagined it. I know someone asked. I know someone. Okay. Well.
Okay. I've always had it set as PDF because for grading, I don't want to have to download anything, and I can grade all the PDFs in Canvas. So.
Oh. Oops.
So if you.
I don't know. I'll talk to you. I'll talk to you.
Okay.
I don't want to hold up the class.
Any other questions right now? Okay. Let's get into lecture then. Okay. You guys can all see this? Guessing. Okay. Sounds good. So we're continuing with filters today. Getting into some of the details of the 3 that we'll be constructing in lab or exploring in lab with simulations, the low pass, high pass, and band pass filters today, getting into quantitatively what their responses are and the like. So I did want to review quickly last week that we did introduce the concept of filters with this schematic here, where you have some signal given over time. It's going to pass through your filter or whatever instrument you're using, and you want to understand what the output is there. Or we said you might install a filter in your circuit to remove any unwanted components of your signals. This could be, the most common use is to remove noise, and we detailed a little bit of white Gaussian noise and what we meant by white being an analogy to light, where white light has all of the frequencies. Here, white noise has all of the frequencies equally distributed, where we showed, if we plot a magnitude versus frequency, that we basically have a constant here. And the Gaussian being that if you took this in time and you have your amplitude or your signal, with Gaussian noise, if you bend this down, if you looked at the distribution of all of that, you would have a Gaussian distribution. And you will be constructing in the lab tomorrow a circuit to incorporate feed white Gaussian noise into your circuit and be able to control that. We introduced the 3 filters we'll be going over and focus more on conceptually talking about mathematically convolution as a way to quantify the performance or how your filter works. In the time domain, we define that as the instrument response function, or in the frequency domain, we define that as the frequency response function that we wrote out as capital Phi of omega here. We discussed that the instrument response function in the time domain is the Fourier transform of the frequency response function in the frequency domain. And overall talked about convolution as a reminder that this is a notation that we're using for convolution, which is the equivalent of taking the integral over all of this virtual space as you shift one signal versus the other in this synthetic time domain T prime here. So looking at the overlap between those two as they're shifted against each other over time. And finally, we talked at the very end of lecture of the way to determine the instrument response function in the time domain for your filter is to send in a delta function into the filter. So if your signal in this notation here of the convolution, if you use a delta function here, we showed like with a very quick proof that then your output would then be the instrument response function itself. So those are all the concepts we went over last week. Maybe I was jumping in between all of those. But the key components here is how you measure the instrument response function by sending in a delta function, and the relationship between the instrument response function and the frequency response function based on the Fourier transform, and which is why Lab 2 was focused on that. So for this lecture, we're going to get into the specifics of each of those three classes of filters that we're focusing on here, with these for each of them discussing these four components. One, if you're constructing the circuit, what electronic components are involved, and you'll should hopefully recognize some of these types of circuits from Physics 122. We'll also describe and sketch out their, we'll mathematically describe the performance of voltage versus frequency with some equations. And we'll also sketch these out and make some plots of what the instrument response function in time and frequency response function in frequency space is. And something that we didn't discuss too much last week, but today we'll also quantitatively define how the phase of your signal shifts in the presence of these filters as well. And while we're going over each of these, after we talk about low pass filter, we're also going to highlight the importance of working in the frequency domain. And oftentimes the frequency response function is measured on your filters instead of the instrument response function. So why is it easier? Why is it better to work in the frequency domain when you're trying to determine the response function as opposed to the time domain? So we'll get into some of the details with that. So that's the big overview of today's lecture. Okay, so jumping into it. So low pass filter, again, remember when last week we talked about this notation of pass and low, high, or band pass, that the low pass means that low frequencies will be able to pass through while high frequencies are removed. And this is constructed with an RC circuit. Where I'll sketch this out, hopefully in an understandable way. Where here's our resistor to be out, and our capacitor. Shown here. So the key thing is where the capacitor is located in here. So the capacitor allows the high frequencies to pass to ground. While the low frequencies go to V out. So if we visually want to sketch this, if we have our signal has these different underlying, if we send some simple sine waves through our filter here. Clearly this is our low frequency signal, higher frequency signal. what will happen for the output, if this is our V in or V out, the low frequency signal will be pretty much unmodified, while the higher frequency signal, depending on where it falls within that cutoff, will be damped, with the amplitude will be decreased. So the low frequency is going to stay the same for low frequency, and the high frequency, the amplitude is going to be reduced by a certain amount, depending on the filter characteristics. And when I say filter characteristics, I'm saying like the resistor and the capacitor you select and what frequency that high signal is. So if we want to define this quantitatively, the performance of what the output voltage will be, we're going to define this based on the capacitance reactance, which is this chi sub C, which is negative I over the frequency times the capacitor here. So that's going to be that reactive capacitance plus the resistance times voltage in. So when we're looking at this definition of this capacitance reactance, there's an imaginary number here. So that's not really our favorite way to deal with things and working with imaginary numbers. So commonly the performance of the low pass filter, that output voltage is reported as the square of the output voltage to remove those imaginary components. So when we square this equation here, what we're going to get is the square of our input voltage times 1 over the frequency times the capacitor times the resistance squared plus 1. So this is the frequency response. Since we have frequency in this equation, this is our frequency response function here. Has this general equation. And do you remember from a past lecture by chance, does this type of form of this equation remind you of any named type of equation that we discussed previously? No one recognizes it. So this is going to be the same as, this has the same form as Lorentzian when we were talking about this. When we were talking about Lorentzians in one of the Fourier transform formats. So you can see here that this is what we defined as the general format for a Lorentzian, shown here. So this is our frequency response function for a low pass filter is going to have a Lorentzian shape. There. So looking at this equation, you can see how this is a low pass filter, thinking about what this equation converges to as you plug in different values for omega here, for your frequency here. So if we have a very low frequency, then this omega CR squared is going to approach 0. So then you would be left with 1 divided by 1. So your V out would be very close to the equivalent to the voltage in. While if you have a very high frequency here, then this is going to be go to the limit of infinity, which would then, with this fraction here overall would go to 0, and then your voltage out would converge to 0 here. So if we want to get more quantitative to it, if we take the square root of that equation, we can say that voltage out is equivalent to close to voltage in divided by the frequency times the capacitor and the resistance. So V out scales as 1 over the frequency. Here. So that's how to look at that equation. So we can plot this frequency response on a log scale. And this is commonly done with the frequency response function, where our log scale here is going to be our decibels. So how the voltage scales on a log scale, which if you can remember from the first lecture, we defined a decibel as 10 times the log base 10 of the ratio of your powers. And then thinking about the relationship between power and voltage, that's also the equivalent of 10 times log base 10 of your voltage squared. Or if you want to simplify that down, it would be 20 times log base 10 of your ratio of your input and your output voltage here. So remember how decibel scales with your the ratio of your voltages here. So if we plot frequency, the decibel scale here versus the frequency, how your frequency response function will look for a low pass filter. It has a general shape like this. This will be the Lorentzian on a log scale, where at a certain cutoff frequency, which we'll define as omega sub c, that's when your signal drops by 3 decibels. Shown here. So that's where your power 3 decibels is when your power, your output power drops by a factor of 1/2, or for your voltage, this would drop by a factor of 1 over the square root of 2. So this cutoff frequency omega c, where you have a 3 decibel drop, is going to be defined by the resistor and the capacitor that you're using. Or that cutoff frequency, which you guys should recall from physics 122, would be 1 over RC. Or if you don't want to be working in angular frequency, we could then introduce the 2 pi here. So that's your cutoff frequency there. Also a feature on this plot, which I also refer you guys to looking at the notes where it's a cleaner sketch than what I'm doing right now, is that this fall off here in the decibel scale also has a slope of -1. Here. So depending where your high frequency component falls after the cutoff frequency is how much, with this little sketch over here, and while I was pointing out how much the amplitude is reduced depends on the R and the C that you have in your circuit. That's what I'm noting here, that if your higher frequency component, something that falls up here will not be as damped as if you have a much higher frequency component as opposed to that cutoff frequency there. Okay. So this is on a log scale, but the linear scale will show you if we plot the frequency response function instead on a linear scale, that's where you'll observe that Lorentzian shape. that you would think of in terms of this equation we defined here. So if I sketch that out, that's going to be our output in terms of volts versus the frequency in hertz. And we're going to have basically half the Lorentzian shape. It's not going to be the symmetric. When we talked about Lorentzian in the Fourier lecture, we talked about, I guess, both that negative and positive side. Here, since we're only working at positive frequencies, is why we're only seeing half of that. There. So you can see that at the top, you kind of have like this rounding at the top, and that's where you're going to have no change in your output voltage. That if we want to say this is normalized, we don't, at the top here, that your output voltage is not going to be changed that much from your input voltage there. So this is the frequency response function, log scale, linear scale, but let's talk about the instrument response function in the time domain. So thinking back to the Fourier transform lectures, if our frequency response function is a Lorentzian, what shape would we expect our instrument response function to be in the time domain? Thinking of the Fourier pairs that we discussed, and you guys should have explored those a bit in lab 2, so it should be fresh in your mind a bit. And remembering the instrument response function is a Fourier pair with the frequency response function. So what shape would you expect, or what type of mathematical function would you expect for the instrument response function?
Would it be exponential?
Yep. So Jack's right. So an exponential is the Fourier pair of a Lorentzian. So we could sketch this out instead. Our output, again, in volts versus time. Here, we would expect to see an exponential decay, where the time constant of that exponential decay will be related to the cutoff frequency here. So if we define our cutoff frequency as 1 over RC, our time constant of the exponential is going to be 1 over the cutoff frequency. So that's going to be equal to RC here. Okay. Okay. So these are the values that you typically characterize for your low pass filter, either in the time domain, the time constant, or your cutoff frequency in the frequency domain. And then the last thing I want to discuss in terms of plotting things is the phase shift of the low pass filter. So not only will the amplitude of your signal be changed, but also the phase of that. And we'll just simply define this and write this out, that it's going to be equivalent to the arctangent of omega RC, or the arctangent of your frequency divided by your initial frequency. So what this means is that at a low frequency, if you plug in different values of your frequencies here, then your phase shift, when omega is close to 0, that means, oh, sorry. Your phase shift, your change in theta is going to be close to 0 at low frequencies. It's going to be 45 degrees at your cutoff frequency. And it's going to be 90 degrees at high frequencies. So if we made a plot of this phase shift, if we plugged in this equation and made a plot of your phase shift, this line here is 0, and we're going to define our cutoff frequency here. What we would see is a shape that looks like this, which is not very nice. Again, look at the notes for a much better sketch. I'm just horrible at this tablet. Where this point here is going to be 45 degrees. And where this plateaus out here at higher frequencies is going to be 90 degrees. Where again, similarly, just like the frequency response here, depending where your high frequency component falls on this slope here, your high frequency components, how close it is to your cutoff frequency will either be shifted completely by 90 degrees or on this curve shape right there. So overall, these are the plots to be aware of. I guess I'll call, you know what, I'll call this 1. On the log scale, frequency response on a log scale is 1A. Frequency response on a linear scale is 1B, because this is the same data just on different axes here. 2 is going to be your instrument response function in the time domain. This is on a linear scale. And then the third one is your phase shift as well. So for all of these filters, it's going to be important for you to know what type of characteristic plot you would expect, and also then to quantitatively know what these time constants or cutoff frequencies are. So are there any questions about the low pass filter so far?
Yeah, could you go back to the previous page? I have a question about one of those sentences.
Mm-hmm.
Okay, so it says that the capacitor allows high frequencies to pass to ground. We probably went over this in the previous semester, but I never understood how it allows that. Yeah. Should we just memorize like how the filter is set up, or I don't know?
Yeah, I mean, I don't have a quick answer to that. So let me think about it, and I'm going to get back to you on that either in the discussion or in lab tomorrow.
Okay,
or
perfect.
not lecture. Yeah, thanks. I appreciate it. Okay. Any other questions right now? Let me make note of that.
I'm only asking this because last semester Dr. Rule put me on the spot and I couldn't answer.
Well, I mean, now you're putting me on the spot, and that's totally fine. And and I'll get, instead of saying something wrong right now, I'd rather compose myself and get back to you. Okay. Anything else? Okay. So with these responses and equations we went over, we were focusing on frequency first, and the frequency response here, and in the plots as well. And typically, I want to make a note of why we calculated the frequency or defined the frequency response function instead of the instrument response function first. And that has to do with like how convolution works and frequency versus time here. That if you remember, we measure our response function by sending in a delta function. I guess we can say it in frequency in time. I'll say it like that. And measure the output in time. So just a refresher of that. And if we look at, we talked about it being convolution, we're back on the first slide, I talked about how the convolution is going to be like an integral type function here. But something to note is that a convolution, if we have two functions in time, and we take their convolution, that would be the equivalent, where this convolution again is that integral shifting the signals versus each other in time. If we take the Fourier transform of this convolution of two signals in time, it's going to be the equivalent of taking the product of the Fourier pair of those signals in the frequency space. Here. So this is a convolution theorem in the frequency. So if we wanted to write this out, convolution of two functions in time is equivalent to the product of their two Fourier transforms in frequency. So I line these up because convolution versus product. It's much easier to take the products and handle those mathematically as compared to convolution. So this is a big reason why Fourier transforms are very powerful. And I'll sketch out here that you can then get that convolution back by taking the inverse Fourier transform. And working in the frequency domain can be much easier when you're defining your response function. If you work with the frequency response function compared to the time domain and the convolution. So that's why when we're defining all this and when you guys are working through lab 3, you're probably going to be working in terms of frequency first instead of in the time scale here. So we can also say, we defined earlier last week that also the instrument response function in time is going to be the Fourier transform of your frequency response function. So we can also define, if we define it, our output as our signal convolved with the instrument response function in time, that would be the equivalent to taking the Fourier transform of your signal and frequency multiplied by your frequency response function. So I guess these little arrows here of the Fourier transform and inverse Fourier transform is really showing that how you go between your output in either frequency or time, but also your signal and your instrument response function, or your signal and your frequency response function here. So this is why we spent a whole lecture focusing on the Fourier transform and that entire lab, because then you're going to be using it in lab 3 and the subsequent labs, because it's a powerful way to characterize the instruments that you're using there. And I've noted here that if you want to go through the entire proof showing that this convolution of two signals is equivalent to the product in the frequency domain, that's all provided in the notes I uploaded. But in interest of time today, I'm not going to go through all of that. But if you do have interest, go ahead, go through that. And if you have questions, please let me know. So any questions about why we're focusing on the frequency domain at all when we're characterizing these. Okay. So we'll move on to the high pass filter then, which simply, again, going back to that definition from last lecture, lets high frequency components pass, filters out the low frequency components. And it's simply, circuit wise, is just going to be that the resistor and the capacitor are switched in the circuit. Here, so we can sketch that out. Resistors here. So then in the same way that we're just switching those components, we can quantitatively define the output for a high pass filter is just going to be your input minus the response of what your low pass filter would be. So plugging in what we define as the response for the low pass filter, and again, squaring this so we're not working with imaginary numbers with the capacitive reactance, what we get is then going to be Vn times 1 minus 1 over the frequency times the capacitor times the resistor squared plus 1 here. Where this 1 in the parentheses here just represents a constant. It's not going to be actually like the number 1 here. That's going to be related to your amplitude, where it's going to represent the maximum voltage output of the filter. Or like what the maximum output would then be, like what your input voltage is here. We can then define the frequency response function similarly. As again, this constant minus the frequency response function of the low pass filter. So based on this, the time constant and the frequency cutoff are going to be the same. So how those are defined is going to be the same. But the behavior before and after that cutoff is going to be flipped based on this. So we can, again, sketch out the frequency response function of a high pass filter. I guess I'll call this 1A here, where we can sketch this on a log scale. So I'm going to write decibels versus the log of our frequency, where we're going to have the slope here and a cutoff turn here, where again, where we have a drop off of 3 decibels is going to be our cutoff frequency, but you have very little, no modulation here of your high frequency versus the slope equal to 1 over here after the cutoff frequency, where again, the cutoff frequency is going to be 1 over RC on this log scale. But you need to know, again, the cutoff or the direction of the cutoff. And then if we sketch this on a linear scale, so I'll call this 1B. Then we're going to have a flipped half of a Lorentzian. I don't know why it disappeared. Based on this equation where you're taking 1 minus that Lorentzian shape here. And then, so that's 1A, 1B. Our plot 2 is going to be our instrument response function in time on a linear scale. And if we look at the equation that we defined for our high pass filter response, we have a Lorentzian over here, and then we have a constant value here. So if we're thinking about our instrument response function in time, and that instrument response function is going to be the Fourier transform of a constant minus a Lorentzian, what's the Fourier pair of a constant? If we just want to think about each of these piecewise, what would be the Fourier transform of a constant value?
You spike at 0 hertz.
Yeah, so what do we call like a spiky looking signal, like a single spike?
Delta function.
Yeah. So it'll have a somewhat delta function shape for part of it. And then again, the Lorentzian portion will show up as a exponential, but here being an exponential rise. So our output versus time on a linear scale is we're going to have a delta function shape at like that time equals 0. It's going to spike down, and then we're going to have the exponential here coming from the Lorentzian. So the delta function here is based on that constant, while the exponential is going to be that similar to the instrument response function of the low pass filter. So in the same way, yeah, instrument response function is constant minus the low pass. So this is showing, again, high frequencies. Conjugate variable means that's going to be very fast time. So it's showing that all frequencies at that fast, the conjugate variable would be passed through. And then at the lower frequency components, that those are going to be modulated much more than, I guess, those higher frequency components. So the best way to think about this instrument response function is to think of the delta and the exponential separately. that your instrument response function for a high pass filter is going to be similar to like convolving a signal with the delta and the exponential separately. And then finally, our phase plot, the phase response. Is going to be the flip of the low pass filter. So we're going to have for arctan, it's going to be 1 over omega RC. And the plot will look like the flip, where instead we're going to be at positive 90 and 45 with the sigmoidal. This tablet is not letting me draw sigmoids very clearly. For the cutoff frequency, you're going to have a 45-degree shift. Low frequency components are going to have a 90-degree shift. And your high frequency components are going to have close to a 0-degree shift here. So any questions about the high pass filter? I think the best way to organize your thoughts is start with the low pass filter, then think of it as just literally switching that resistor and capacitor, then leads to this mathematical, I guess, just flip or shift within the equations. So keeping those things straight when you're taking the quiz or working on lab 3 of knowing, okay, with these cutoff frequencies or time constants, or again, the time constant here of the instrument response function, what those are defining based on the location of those electronic components. Any questions? Okay. We'll move on to the last portion then of bandpass filters, where these are going to be a little different. So I want to highlight that the high pass filter and the low pass filter that in Phys 122, you guys should have explored those with the RC circuit lab. And here for the bandpass filter, that's going to be for the LCR circuit lab. That you have an additional component here with the inductor. So we have our Vin, our inductor, capacitor, and then LCR circuit. Well, just like with the high pass filter, so the role of the capacitor, just like in the high pass filter, is going to block out the low frequencies. While the inductor is going to block out the high frequency. And the frequencies that are in resonance with the inductor and the capacitor is what is allowed to pass. So again, thinking about LCR circuits are similar to damped oscillators, which you guys should have explored in that past lab. So in resonance, thinking of this as a damped oscillator, that's what's passed. So the bands typically end up looking like you're going to have some type of peak where instead of defining, there's 2 definitions here that differ compared to the low pass and high pass filters. That you have your center frequency here that we define as omega naught, which is going to be 1 over the square root of LC. And then another thing is the width of your band that's allowed to pass, this delta omega. So delta omega is typically defined relative to your center frequency here, and that's called the quality factor. or Q. And that's going to be your center frequency, omega naught, divided by delta omega, the width of your bandpass filter. And this is going to be defined as square root of L divided by C all over R. It's your quality factor here. So in lab 3, you're going to explore, I guess I changed it this year. Normally you would have been constructing your own circuit there. For a bandpass filter, this year I'm providing you guys with some information, but how hypothetically to reach a certain quality factor versus like the actual performance based on some capacitors and inductors that I used there. So again, getting to our plots of the performance of these and equations, we can talk about the frequency response function. Which we're going to define as 1 divided by the square root of the resistor squared plus your frequency times the inductance all over 1 frequency times the capacitor squared here. Which will then give you a shape similar to that. Versus frequency. So when you're looking at this equation here, it's important to note that this is not a Lorentzian. You might be tempted by that, given the shape where we have the square at the bottom is shown. And one way to think about this output is it's very similar to a convolution between your instrument response function of a high pass filter and a low pass filter. Remembering that you take the product between the frequency response functions when you're performing. If you're in frequency, it's the product between the two will get you your frequency response function for the bandpass filter. That looking at the shape over here, it has a zero-ish shape. As your frequency is low or high, your output's gonna be close to 0 versus the center frequency here. So we're just going to focus on the frequency response here and then the phase response. Where I'll first define the phase response. It's going to be the arctangent of your frequency times the inductance minus 1 over the frequency times the capacitor all over the resistance. So then if you plug in different frequencies here, you'll have either a high shift at low frequencies or at high frequencies, and right at your center frequency here, you'll have 0 degree shift. So it's going to be 90 degrees or negative 90 degrees, but based on that center frequency, how you design your bandpass filter, you'll have no shift, 0 degrees. Not the most symmetric plot here. And if you plug in omega naught in here, what this will condense down to at omega naught, that's going to be close to 1 over the square root of LC. So that's how your theta goes to 0 over there. Yeah. I think Any questions with the bandpass filter then? Okay.
That first graph is the output in dB or just volts?
No, so this one will be just in volts here. Yeah. But I've shared less plots here for the bandpass filter, just focusing on the frequency response function and the phase response. Let me look if yeah. Because this isn't quite, I think, thinking in terms of, okay, if we want to take the Fourier transform of this, it's not going to be like a set defined shape or function. So that's why I haven't sketched it out here. So I guess it would be, that's why I've been focusing in the frequency response function. It's easier to sketch out what the product of a high pass, low pass filter would be, but there's no like set easy way to sketch that out in the time domain, I guess. Yeah.
So it's not explicitly stated here, but so I just want to confirm, is the way you change delta omega with the resistor?
So it's going to be with the inductor and the capacitor here. So this equation here, omega naught, 1 over the square root of L and C here. But so that's where you'll define, that's how you'll define what your center frequency is. And then selecting your resistor relative to those will define like what your width is.
Yeah, okay, yep.
Any other questions? Okay. So I know this is a lot, kind of a lot to digest, but I think the takeaways is Lorentzian for low pass and high pass, an exponential in the time domain, and depending on if you're cutting off high or low frequencies based on where that resistor and capacitor are the takeaways from those. And then that the bandpass filter is uniquely different, that you're going to be working with the LCR circuit, and just like Gabe's question pointed out, the combination of those threes will define the center and the width there. So next lecture, we're going to have some more time, I guess, to go as a refresher for this. I think Gabe's question makes a good point that I'll probably get into more of like how the electronics block either low or high frequencies based on that circuit. And we'll do a little bit of a refresher of these. There's not going to be a lot more additional content next week. So we'll be able to do a refresher of this, and hopefully you'll digest a bit more, and you'll actually have started lab 3. So that's what we'll highlight next week. Again, I wanted to point out in Canvas, if you want to provide some feedback, you can do so there. And then these are the same resources that I posted last lecture. Doesn't hurt to take a look at some of those old labs that you took in E&M. And this is again focusing on the convolution. So I think that's most of what I had. I'll stop the share. And anything else? Questions, things people want to discuss? Okay, sounds good. So we finished up a little bit earlier. So I'll encourage you guys again, take a look at those LCR or RC labs. Would be a good, nice thing to do before tomorrow's lab. But I'll see you guys tomorrow. And I think I also have to make a sign up sheet on the Google Doc form. So I'll also do that so you guys can sign up for your lab partners as well. Okay.
Can I stay back and ask a few individual questions?
Yeah.
Thank you.
Let me stop recording first.